So in this lesson, we are going to talk about a review topic. Every so often, one of our lessons will be just a little review, something I saw that I thought you needed just a little more help with. So let's talk about interval notation. We already have been doing it, but we're going to start applying it more to domain. So domain is the set of all of the x values that we can use. Now remember, there are some functions that have x values that we need to eliminate. Fractions, we can't have zero denominators. Square roots, we can't have negatives. If we're talking about the real number line. Range is a set of output values, the set of y's. So what numbers can we get out? Now, domain, we can sometimes figure out algebraically ahead of time without looking at the graph. But range, we're kind of going to have to rely on the graph. So really kind of expect that range will rely on the graph a little more than domain. Domain, we kind of can expect some things. Interval notation, remember, is a way to properly depict a subset of the real numbers. It's a portion of the real number line. I noticed on the last test or quiz that some of you were not putting your interval notation in number line order. It is depicting where you started on the number line on the left and where you stopped on the number line on the right. So it goes number line order. Okay, so that's super important. Number line order. So please remember that. It's always going to follow the number line. Remember, we put a bracket in an interval if there was an equal to. We put a parenthesis on an interval if there's not an equal to. An infinity symbol, we can never be equal to that. So that's a way to remember. An infinity symbol always gets a parenthesis. Okay. So this should be review, I would assume. If not, hopefully this will just reinforce what we've talked about in the past. So let's do a few just to make sure that we're on the same page, okay? So if you see x is less than 2, do you see how the arrow here, see how this points the same way as that? If the x is on the left side, that is an indication that can kind of tell you that's the less than symbol. For those of you, if you were having difficulty with that. We're going to put an open circle at 2. We're going to shade to the left. Okay. Now remember, interval notation follows the number line that you colored in. So we start, the leftmost point is negative infinity. We stop but cannot stand on 2. So that's like the point 1.999 is okay, 1.999 is okay. To indicate that we're every value but 2, all the values leading up to 2 but 2. So I call it almost 2. We indicate that with a parenthesis. Indicate that with a parenthesis. Okay. Now, let's look at the next one. Greater than or equal to negative 2. Color in the dot at negative 2, shade to the right. Now we're following the number line order. Can we stand on negative 2? Yes. So we put a little bracket indicating, oh yeah, you're allowed to stand there. That value works. And then where are we heading? Well, we're heading to infinity. Infinities always get a parenthesis. Let's do the next one. X is less than or equal to 0. Equal to 0 means put a closed-in dot. Less than, shade to the left. Follow the number line order. Our leftmost point is negative infinity. Our rightmost point is 0. We are allowed to stand there. Put it in a bracket, meaning there's not a hole there that I can fall through. Okay. Now, if we have a betweenness sort of idea, like the last one, negative 2 is less than or equal to x is less than 5. It is customary that these should both be less thans, okay? Because if we look at this direction, That means that x is greater than or equal to -2, but also that x is less than 5. It's a intersection of those two things. So that's why it's all the things between those values. Now, are we allowed to stand at -2? Yes. So put a bracket there. On the graph, we're going to put a closed-end dot. Are we allowed to stand at 5? No. So put an open circle. We're going to shade everything in between, and then when we put it on our interval notation to indicate we're not allowed to stand there, we're going to use a parenthesis. Okay, so I am hoping that that just reminds you how those works. Yes. Oh, that's going to be a bracket. Okay, so if you are equal to something, put a bracket. If you don't have the equal to symbol, put a parenthesis. Okay. Any other questions about those four? Okay. So let's just look at two more examples before we move on to the next thing. So this is set builder notation. Set builder notation just includes, the only difference from what we just saw in set builder is this little notation here. It's got a bracket, the wiggly brackets, and then it has that line. This line means mathematically, if you were taking an upper level math course like at a university or something, your professor would read that as the words such that. So what does that mean? I want the x's, the set of x's. That's what the first part means. This is what you want. I want x's such that the x's are greater than 3. That's how you technically, the mathematical way to read that. I want the x's such that x is greater than 3. All you got to focus on is the greater than 3 part. Okay. So when we go to put it on our graph, we would have an open circle on the 3. We would shade to the right. Now our interval notation needs to follow that. So we're going to have a parenthesis on the 3. We are going to infinity. Okay. And then we have been doing some where we had to solve them. So let's just practice one more that we have to solve. Now the only key is, the only time we flip the symbol is if we divide by a negative. Some of you, when you were taking the quiz or test, you just flip the symbol if you divided by anything. It has to be a multiplication or division by a negative, okay? So just be careful with that. So I'm going to solve it over here to the right. I'm going to subtract 2 from both sides. There is still a negative in front of my x. So here is a perfect time that when we divide by that negative, you have to remember to flip over that symbol, okay? That's the only time when we multiply or divide by a negative. Now, if we have to turn it, it stays where, the point stays where it was, but we're not turning it here. We're flipping it because of the division by a negative. And so we get x is less than or equal to 5. So if we want to put it on the number line, we're going to have a closed-end dot at 5. We're going to shade to the left. So we're going to go from negative infinity up to 5. We're allowed to stand at 5. So we're going to put it in a bracket to say, hey, I'm allowed to stand there. Okay. So hopefully that is just one more little kind of reminder of how interval notation works. It's not going to go away. The more we explore domains, the more we will be using interval notation. It always follows the number line. It is always when we've colored in some portion of the number line. Everybody good with that one? Okay. So that is just a very simple practice your interval notation. So now we would need to finish this up. So if you could please continue on to 3.1d. So we're going to be talking about what a root or a zero of a polynomial is. Well, a 0 or a root of a polynomial is where the function equals 0. So technically, we could even write that as y equals 0. On the graph, we know what that is already. That is an x-intercept. So what we're starting to do is we're starting to gather more and more information about what our graphs are going to look like. And the zeros tell us a lot. And especially if you ever take calculus in your future, the zeros give us a lot of information. So in our first example here, where it says to solve for v, you may notice that it is equal to 0. Now that is one of the first things you want to make sure when you try to solve most equations. Setting it equal to 0 is very helpful, unless it's a very simple one variable kind of equation where you don't have any powers, like just a linear type of equation. Then you can solve it the traditional way, get the x's to one side, numbers to the other. But here we've got powers, we've got things with our v's. So when you want to solve a problem like this, the most effective way to solve it is to factor it as far as you can go. Before you do anything else, as long as it's equal to 0, okay? So we're going to factor as much as possible. So one thing I have noticed on this problem is that this portion right here is not factored. So in order for me to complete this problem, yes, that piece alone can be solved with the quadratic formula. But if I can factor it, it's going to make my life so much easier. So factor it. Make that v plus 5 and v plus 1. Now, why? Because 5 times 1 is the 5 on the end. 5 plus 1 is the 6 in the middle. So it's a factorable quantity. Now, I had one like this on the last test, and some of you wanted to remultiply it. Well, no, this is the greatest, form you want when solving an equation like this, because it actually tells us that there are going to be 3 possible answers, and we can just split it up and make 3 very simple equations at this point. So what we're going to do, once you get it to this point, you've got it. You're so close to solving it. You're going to set the 3v plus 15 equal to 0. So that's this one. You're going to set the v plus 5 equal to 0. That's that one. And then you're going to set the v plus 1 equal to 0. Now, the reason you do that is because if things multiplied together and got the answer 0, any of those things could have been the culprit. And so by the zero product property, you get 3 possibilities. So this one is that 3v equals negative 15. So v is negative 5 is one solution. V is negative 5 here is another solution. And v is negative 1 here is another solution. Now, this one could have been factored more. We could have taken out a 3. And then you can see where that negative 5 was hiding, okay? So technically, do we have to write it twice? No. The roots are going to be negative 5 or negative 1, okay? Because there was a repeat, it does tell us something that happens at the graph there. Anytime we have something that repeats an even number of times, a root that repeats an even number of times, if you were to put this into Desmos at negative 5, instead of going through the x-axis as an x-intercept, it bounces off the x-axis. So it is going to tell us something when that happens. So it is something for the future. For now, you only have to list it once. Everybody good with that? That one there. Okay, let's look at the next ones. So it says to find all zeros of the quadratic function. Now remember, zeros are just your x-intercepts. So that's where y equals 0, or the function equals 0. So you're just going to set x squared plus 9x minus 36 equal to 0. Where is the function? Where is the y equal to 0? So anytime they say zeros, that's what they're looking for. It will tell us where we hit the x-axis. Now, 36 is 6 times 6. Doesn't add up to 9 or subtract to 9, actually. It's actually negative 36. We could use, yeah, thank you. I was getting there. We can use 3 and 12. 3 and 12 multiplies to give us the 36, but has a difference of the 9. So this is factorable to be x minus 3 and x plus 12. Now, remember, to solve any quadratic, if you can't see the factorization, feel free to use the quadratic formula. It would work, but we get x minus 3 equals 0 gives us a 0 of positive 3. X plus 12 equals 0 gives us a 0 of negative 12. So see where it says separate them with commas. So you would put 3 comma negative 12 for Alex. Any questions about those ones? So factor them. If they're equal to 0, factor it if you can. If it is an irreducible quadratic, meaning your quadratic is not factorable, feel free to use the quadratic formula on that. Any questions about that one? Okay. So even one that has multiple pieces like we see here, doesn't matter. The factored form is the greatest form, okay? So let's write down, we want negative 5x times x squared minus 25 times x minus 6 to equal 0. Does anybody notice a piece that can be factored? Is there? Yeah, no, there's a piece that can be factored. X squared minus 25 is the difference of squares. Now, if you set that piece equal to 0 on its own, you would probably recognize or get to that when you take a square root, put a plus or minus in front. But you could also, bless you, you could also break it apart ahead of time. The more it's factored, the better it is for you. And so we would get x plus 5 and x minus 5 in any order. Now that it's in factored form, the greatest part is it is now so easy. That's the hard part. Get it in factored form, and then each factor we're going to set equal to 0. If there is an x out front, I put any numbers that are there with it because we'll just divide them off. So here, if we divide by negative 5, 0 divided by anything, still 0. 0 is allowed to be your answer. Some of you were a little concerned if you got an answer of 0. That's okay. It's just a number. Here, subtract 5. Here, add 5. Here, add 6. You might notice the pattern here. It always ends up being the opposite sign that we saw in the parenthesis. That is no coincidence. When it is a factored form like this, when we go to solve it, it should end up becoming the opposite sign that was in the parenthesis. So those, you're going to have to list 4 of them. What that means is this graph hit the x-axis in 4 different places. If you were to type this into Desmos, you would see that your graph does indeed hit the x-axis 4 times. Okay. Any questions about that one? Okay. So let's take a look at our homework that matches this, okay? So you'll notice it's in factored form already. So our first problem here, let's do that together. We're just going to set 2x minus 1 times x minus 5 equal to 0, which allows us to do 2x minus 1 equals 0 and x minus 5 equals 0. And then you could just solve those very quickly. So 1 through 6 are very, very easy to do. They're in factored form. 1 and through 4 down at the bottom are almost all factored. We have some things that could break down further. Could we please do number 1 right here together? We're going to do that one. The one down at the bottom where it says find all solutions to the equation. Now, technically, this factors to be x, well, it does factor, but just to show you something. Okay, so if we set the first piece equal to 0 and the second piece equal to 0, something happens for each. So let me show you. This is going to be x squared equals 6, or x equals plus or minus the square root of 6. There are 2 solutions. You can really factor x squared minus 6 to be x plus the square root of 6 and x minus the square root of 6. It is factorable. Some of your algebra teachers, rightfully so, just to not mess with your brain when you were younger, says that they both have to be perfect squares. They don't. Is square root of 6 a legitimate number on the number line? Yeah. So can you make it x plus square root of 6 and x minus square root of 6 to show that there's 2 solutions? Yeah, you can. Let's talk about x squared plus 1. That's actually factorable too, but it's only factorable with i's. So that would be x plus I and x minus I. So when we go to factor that, why does that happen? Well, you get x squared equals negative 1. So x is plus or minus the square root of negative 1. What is the square root of negative 1? It's an I. So that's x equals plus or minus I. Now see where it says find all solutions? That means that include the i's. If it just says to find the real solutions, or to find the zeros. Zeros mean real. That means they really touched the x-axis. So we don't have to include i's when the instructions say that. But when the instructions say find all solution, please include the i's. Okay. The i's don't show up on our graph. They're not a real number line point. But okay. So there is that. Yes. Oh yeah. So for those ones, it doesn't matter how many pieces we got. You're just going to split each piece apart. So like for 5, we're going to do x equals 0, x plus 2 equals 0, x minus 2 equals 0, 3x squared minus 4 equals 0. Now, if you know where 3x squared, how 3x squared minus 4 breaks apart, you can split it into 2 pieces. But if not, think about that's the hardest one to do. Think about how you do that. We're going to add 4, divide by 3. What's going to get rid of a square? What's going to get rid of our square? Square root, what do we put in front of it every time? Plus or minus. So this is x is plus or minus the square root of 4/3. Now let's talk about square root of 4/3. What the heck do we do with that? Because it's funky. Technically, you should square root the top and square root the bottom independently to see what you got. So this is technically 2 over radical 3. And then I'm going to show you a trick. I'm okay. That is the answer. But we were told in algebra, we never want a radical in our denominator. So this is what's happening. If you rationalize it, we multiply top and bottom by that thing. And what we get is it actually just pops to the top and leaves a normal 3 behind. That always happens. Like, 7 over radical 2 is 7 radical 2 over 2. It just pops the radical to the top and leaves a normal number behind. So if you know that pattern, you can take this and switch it to that very quickly. That pattern always happens. Okay. So that is 3, 1, C, and D. Okay. Unfortunately, I want to do one more thing. so I can give you time to study it, okay? We are going to be focusing on the 9 graphs that you see here called the parent functions. We are going to be using them all semester. If you take calculus in your future, these 9 functions are super important that you have them. We will have a parent function quiz, just a memory quiz. I will hand you this exact paper and you are going to duplicate it, okay? So this is what you need to know. It's going to look exactly like this. I'm going to print this out. I'm going to hand it to you, okay? The constant function, you're going to write y equals c. You're going to pick any number on the y-axis. I don't care where it's at. It can be in the positive section, negative section, I don't know. And you're just going to call that c. I don't care where you put it. Put it wherever. And you're going to draw a horizontal line there. We know y equals a number is a horizontal line. And then, so if I plug in -1, I get c. If I plug in 0, I get c. If I plug in 1, I get c. That is your constant function. Again, feel free to put c anywhere you want it. I put it at 3. It doesn't matter, okay? What you need to know for identity, the identity function is y equals x. Any identity is something that doesn't change the value of it. So that's why you can remember that y is equal to x. The identity of x didn't change. So if I plug in -1, I get -1. If I plug in 0, I get 0. If I plug in 1, I get 1. And just plot those points. You know how to graph y equals x. It's just a straight line. That's it, okay? The table will be there for you. The graph paper will be there for you. You have to give me the equation, the graph, and the table. Equation, the graph, and the table each time, okay? Let's move on to absolute value. That's y equals the absolute value of x. The job of an absolute value, if I plug something in, whatever that answer is inside, it makes it positive. So if I plug in -1, it's going to turn it into a 1. If I plug in 0, it's going to be a 0. If I plug in 1, it's going to be 1. So just let's put those points on there, and then we make a graph. The graph of an absolute value is a perfect V that splits the first quadrant and splits the second quadrant. Perfect V. The first quadrant has a slope of 1. The second quadrant has a slope of -1, that portion of the line. If you want to get yourself a bonus point on the quiz, you can know that it's technically a piecewise function. It is the opposite of x if x is a negative. It is the same as x if x is greater than or equal to 0. That piecewise function is something that is helpful to know if you take a calculus class. That piecewise function is helpful when you do something called a derivative. But if you know it for me on the quiz that is coming up next week, you can get yourself a bonus point. Okay. So those are the first 3. Now let's talk about reciprocal, quadratic, and cubic. Our reciprocal function is y equals 1 over x. Want to get yourself a bonus point? You can also say y equals x to the -1. Those mean the same thing. A negative exponent's job is to flip something, make it the reciprocal. That's why it's called the reciprocal function. If we plug in -1, we get -1. If we plug in 0, it is undefined. If we plug in 1, we get 1. So how do you make the reciprocal function? Now we're going to explore how to transform these functions. That's why we need to know the basic, what's called the parent functions, okay? So the first thing I want you to do for the reciprocal function is I want you to make a dotted line down the x-axis and y-axis, because it's undefined at those places. You're never going to get out an answer of 0. You're never going to input an answer of 0. Now let's put on the point 1, 1 and the point -1, 1. Now I am not great at making these look pretty, but let me kind of describe what they look like. A very rounded L in the top first quadrant. So this piece is getting closer and closer to that axis. This piece is getting closer and closer to that axis. Now this is an odd function that has what's called origin symmetry. You can spin it around the origin and it will look the same in the third quadrant. So this one heads to this axis, never touches it. This one heads to this one and never touches it. So it looks something like rounded kind of L's. So that is our reciprocal function. Now let's go to our quadratic function. Our quadratic function is y equals x squared. You should know by looking that that's a parabola. Okay. If I plug in -1 in parentheses and squared, I get 1. 0 squared is 0. 1 squared is 1. If you want to be more accurate for a parabola, if you plug in 2, you get 4. If you plug in 3, you get 9. Do you have to plug those in? No, it's helpful. Kind of tells you the width of the parabola. It has y-axis symmetry. I could fold it across the y-axis and both sides look the same. So that is your quadratic function. The cubic function is y equals x cubed. If I plug in -1, I get -1. If I plug in 0, I get 0. If I plug in 1, I get 1. So in the first quadrant, it looks just like a steeper quadratic. In the second quadrant, it stays negative. If you cube a negative, it stays negative. So that's why it goes to -1. So that is your cubic function. So those are the next 3 that you're going to need to memorize, okay? Again, I'm going to give you this exact paper. Nothing's going to change. I'm going to hand it to you. You're going to spit them out, okay? It does help. Now, let's compare our reciprocal function to the one underneath it. Those two kind of go together. So this is y equals 1 over x squared, or y equals x to the -2. Get yourself a bonus point and write down y equals x to the -2 as well. When you square a negative, it does become a positive. That's the difference. So this is 1 undefined 1. It's different. We still can't have the x-axis or y-axis. So you still want to make that dashed line along your x and y axis. But at 1, we're at 1, and we're at -1, we're also at 1. So what happens here is it becomes symmetric about the y-axis again. We still have that kind of L going on here, but you have its mirror in the second quadrant, because that squared pops that negative portion up and makes it positive. So that is the difference between a reciprocal and a reciprocal squared. This one, that piece becomes a positive. When I square something that's negative, it becomes a positive. Okay. Last 2 that you have to have memorized is our square root and our cube root function. And I'm going to change, and I should have done it. I didn't even think about it. Our square root function is y equals the square root of x. If you write x to the 1/2 power, you can get yourself a bonus point. Now, this is undefined. You can't plug a negative in there. Sorry, I didn't even think about that at the time. But the square root of 0 is 0. The square root of 1 is 1. I'm going to put one more little point on here. I'm going to put the square root of 4 is 2. So I'm going to just extend my little chart a little bit. You don't have to. It's helpful. It's helpful. So at 0, I'm at 0. At 1, I'm at 1. And if you go to 4, I'm at 2. That's your square root function. It is undefined over here. There are no negatives that make it work. So it starts at 0, swooshes over. Swoosh to the right, I call it. The swoosh to the right. So that is our square root. Okay. And then the last one I want to do is our cube root. So that's you put that little index of 3 to indicate a cube root. Get yourself a bonus point if you call that a 1/3 power. They mean the exact same thing, but there are going to be some things we're going to do later on where the 1/3 power is helpful when we do some stuff to what's called a power function. If you plug in -1, the cube root of -1 is -1 because -1 times -1 times -1, -1. Cube root of 0 is 0, cube root of 1 is 1. It looks super like a square root. This piece still swoops to the right. But you got an extra little piece down here. So that is our square root and cube root function. Okay, so plan on having those memorized early next week. We, at the beginning of class, probably Tuesday, I'll hand it to you. You'll fill this paper in pretty much exactly what you see here, okay? Any questions about any of this stuff? You have the remainder of class. You have a lot of stuff to work on. Remember, you have Achieve, you have Alex, and you have all of the 3-1 pieces and parts. Each one has only, it doesn't have a ton of problems. So, but they're all due tomorrow by midnight, Saturday by midnight. Okay, there you go. Do your thing.